So, I want to convince you. I want to convince you that objects oscillate freely at natural frequencies particular to the object. If the object is driven or forced at its natural frequency, then it will oscillate with a large amplitude. It will set up something we call standing waves, and it will undergo the phenomenon we've referred to as resonance. The natural frequency for any object is predictable, and I want to convince you of this too. And it's largely based on the geometry of the object. In particular, if you change the geometry of an object, you will change those natural frequencies at which it prefers to oscillate. Sounds like a lot, but let's put it in short. In short, objects shake wildly only if you fit chunks of waves into their shape. Now, does that make you feel any better? We'll see. I mean, first off, who cares? Well, here's one reason to care. This is really the beginning of quantum thinking. We're not going to learn quantum mechanics right now, but it's the same concept. And that is, there's only set-sized chunks of energy that can naturally exist in an object. A fancy word for a chunk of energy is a quantum. And there's another reason you should care. Predictability. You see, if you know about these chunks that fit naturally into a shape, you can then predict what will make that shape shake wildly. Who needs to know that? Well, designers, musical instrument designers, swing set designers, earthquake-proof building and bridge and road designers, microwave oven designers, tennis and golf ball designers, as well as tennis racket and golf club designers. List goes on because it truly is everywhere. So back to where we started. I want to convince you. I'm going to try to do it with two live examples. Example number one is right here. We have a string under tension. It's got a little vibrator here that I'll show you, and a little generator here. And the second is a pipe instrument. That's it. With these two alone, I want to convince you what resonance looks like, what standing waves look like, that chunks of waves fit naturally into an object based on its geometry, and that's how that object likes to shake. So, let's get right to it. First object. Bring you over, let's have a little inspection. Here it is. So we have something called a mechanical vibrator. Here it is. This little piston can move down and up. In fact, it is driven, so it's not powered, it just shakes. It's like a speaker. You connect it to a generator, a signal generator, and when you turn this thing on, it basically sends a signal to shake up and down. So let's turn it on. And we can start to turn this thing up, and you're already seeing some action over here. Let's not worry about that. Let's look. See that little guy shaking up and down? See a little blur. This piston right here is moving up and down. Okay, good. Now what we have in it actually is a wire. Now, it's actually a string. It's a stretchy string, an elastic string. Now I've run it a full 1.6 meters from end to end and centered this generator right here at about 0.8 meters. Now it has a screw Loosen that up so that there's no tension. This string can move freely between here. And down here on the end, we have a hanging weight, 50-gram hanging weight. That puts tension on the string. So the string should have the same tension all the way through its length. So now, we'll clamp this down. And what we're going to do is turn this on. And something pretty neat happens, you'll see. The two sides of the string, let's say our left side and our right side, should be equal in every way. Same length, same tension, it's the same string, so the same thickness. Well, let's see what happens. What we're going to do right here is we're going to take our generator and let's turn it on. We're going to start it down at 1 hertz. Look at our wire. Is it shaking? Well, yeah. A little bit of wobble there. Nothing much to see though. So, what about if we turn it up? Well, let's turn it up. 2 hertz. 3 hertz. And I'll keep saying them as I'm counting it up. And you'll see if anything interesting happens. 4, 5, 6. You can see that little piston moving faster now. 7 hertz. That means 7 up-downs per second. 8 hertz. I have the amplitude turned all the way up, so that's as wild as it'll shake. But at 8 hertz, this string is not doing anything magnificent. 9, 10, 11, 12, 13, 14. Uh-oh. What? What just happened? Suddenly, around 15 hertz, this thing is shaking. Let's try 16. Oh my, what? Look at this string. A couple of things to note here. Number one, both the left side and the right side are exhibiting this large amplitude vibration at 16 hertz. Now, it may not be exactly 16 hertz because this thing only goes out to the nearest 1. It doesn't give us decimal places. It may be 15.8, it may be 16.2, but there it is. Actually, if we put this in video mode, you will see, there you go. You can kind of see what's going on here. The string is vibrating rapidly between those positions. In fact, if we go to slow-mo, you can almost see the breakup of the string a little better. So the string not in multiple places at one time. It is in only one place at a time. There we go. And when you're in photo, it looks kind of blurred. But if you put your finger here, don't get cut. You stop this. Okay. So pretty cool. So what this is saying is that 16 hertz, roughly, is a natural frequency for this string in this orientation. Now, do you notice a chunk of a wave? Well, actually, you are seeing half of a wave on each side. So here on the left, you're starting from a point of no movement. You're ending here at a point where it's pinched, no movement. And you see either a crest or a trough. It's not both at the same time. It's oscillating between the two. So here, what you're doing is you're actually seeing, if we sketch this out on the table, over here it's not moving. We're going to put an N for no movement. Over here it's not moving. We're going to put an N for no movement. And between the two, we are getting this path that kind of looks, this little guy's in the way, kind of looks like this. Or, put a dash, this. There you go. Same thing on the other side. And here's the thing about it. What have we fit in there? That is actually 1/2 of a wave. That's 1/2 of a wave you see there in front of you. And so 1/2 of a wave, it's either a crest or a trough. Same thing on this side. Well, when's the next resonant frequency going to come about? Remember I told you this will only naturally fit chunks of waves. Well, if it had 0 before, it chunked up by half a wave. What do you think the next chunk will be? Let's try it out. Here we are at 16. Let's go. 17. 18. Interestingly, notice the amplitude has gone down. 19. 20. We're at 21. Notice higher frequency and nothing's really happening in the string. 22. 23. 24. 25. We are not at a natural frequency for this string in this orientation, which means it is not going to oscillate with a big amplitude. You are not going to get a standing wave. 26, 27, 28, 29, 30. Oh, I'm starting to see something. 31, 32. Look at that. At 32 hertz on both sides. Oh my goodness, would you look at that? Let's try this thing in video if we could see it broken up a little bit. There, you can kind of see this string. There's almost a shadow there you can follow. Where it's moving, it's either up, down, or down, up. You can follow, you see it nicely on this side. So we have just chunked another half wave into that position. Pretty cool, into that string. So now we have another resonant frequency at 32 hertz. Well, no surprise, the last one was at 16. Oh, we're starting to see something here. Oh, this is interesting. If we do a throwback, we have this equation. Speed is frequency times wavelength. And if you remember, the speed depends on the medium. The speed depends on the medium. Did the medium change? No. It's the same string under the same tension, which means the speed depended on the medium, which means as the frequency goes up, the wavelength will go down, and vice versa. And this makes sense. Before, in this 0.8 meters, we fit half a wave, which meant the wavelength at that point was 1.6 meters. Now, this is a new picture. In fact, we can draw it right here. Pardon me, instrument. So we have no movement. We also have no movement here in the middle. And we have no movement. Ooh, watch out, our little speed equation. Down here again. This time, the pattern looks like this. Up. And then we get our down. We're going to run into our equation, but you see where it goes. Or we can have the dashed version, because it's either in one of those two or in between. If you notice here, how many waves have we fit? This one is now one full wavelength. That's one full cycle, which is 0.8 meters. Well, what a surprise, what a surprise. Sorry, that looks terrible. 0.8 meters. There we go. We have halved the wavelength. And so from this equation, halve the wavelength, you should double the frequency. Boom, 32 to 16. It's doubled. Cool. We found a second natural frequency. This string is called resonating. And what you are seeing in front of you, the wave looks like it's not going anywhere. It's just standing still. And so we call it standing wave. All right, any predictions on the next one? Being that we are adding half chunks, well, let's go up one more. Why not? Can we fit another? Well, if we start going up, 33, 34, 35, 36, look at our string. Nothing. The amplitude is basically gone. What's happening here? Answer, destructive interference. Destructive interference. This does not naturally fit within that length of string. This length of string likes to vibrate with a big amplitude if you fit chunks of half wavelengths. So let's keep on going. Of course, we had one chunk, which was half wave, two chunks, which was a full wave. Let's get some three chunks in here. Why not? Come on, where are you? Woo-wee! There it goes. Look at that. Pretty as a picture. And on this side. That is fantastic. Look at that there. And so, what you're seeing here is one more sketch on this side. We got no movement all the way down on the end. And now we have a new point of no movement right around here. A new point of no movement right around here. And right back here. So this time we have 1, 2, 3, 4 points of no movement. And the connection between them is it's connecting chunks of half waves. So there's a half wave. There's a half wave. There's a half wave. And sometimes we draw it back like this. It's kind of standard standing wave notation. Pretty cool. And so in this case, we now have 1 1/2, I'll write 1.5 waves. And so the wavelength will be, well, the wavelength in this case now is, the easiest thing we could do is way back when, distance over cycles. So 0.8 meters over 1.5 cycles. Basically 2/3. And so this comes out to about, let's see, maybe 5, 4, something like that, meters. And of course, no surprise, frequency jumped up another 16 hertz to 48 hertz. So you see in the rhythm here, I wanted to convince you, only natural frequencies. When you drive an object at its natural frequency, will it set up standing waves and resonate at a large amplitude. How do we find those? Only chunks of waves fit in. This one, when you have a string with a pinched end and a pinched end, such as a guitar, such as a violin, such as a banjo, or a cello, or a bass, it will vibrate like this in half chunk waves. In fact, this is called the first harmonic, or fundamental, second harmonic, third harmonic. Believe it or not, they're all happening when you strum your guitar, but primarily it's this one. Then there's a little bit of this one, and then even less of this one. This is the main one happening whenever you play your stringed instruments that are pinched at both ends. So we don't need to see the math anymore. Let's just bump it. 48, you know the next one's gonna be 64 by now. Let's run with it. Let's just jump right up there. Come on, 64. Boom. Look at that. Woo-wee. Pretty cool. This is fun. You know, you can keep going with it. What comes after 64? Should be right around 80. And there it is. 1, 2, 3, 4, 5. This side too. Oop, this side's a little bit off. And there it is. This one hits it at 79. See, it's slightly off center. Slightly different. So, pretty cool. This all worked out. Now, one thing to notice here is I told you it depends on the object. So turn the amplitude down a little bit. There we go. That's so noisy. If you change the object, you change its resonant frequencies. Well, how can you change the object? Here's one way. If it's a string, you've done this before. Let me lower this down. So we've settled down back to 16 hertz, and we picked that on purpose. Instruments, stringed instruments in particular, like to oscillate, like to vibrate at their fundamental harmonic, or first harmonic right here, just like this. In fact, we saw it over here. That first half chunk wave, that one quantum, is really the way instruments like to vibrate. So let's talk real quick about tuning instruments. Well, change medium, change wave speed. Let's change the medium. One way to change the medium is to add tension to the string. So here's a little mass, 100 grams. This is going to pull it all the way to the ground. Get on down there. Good. So we know for certain we have added tension to this string. And by adding tension, oh, look at that. We've killed the standing wave. So we can analyze this pretty easily, actually. So based on our equation, speed equals frequency times wavelength. If we change the medium, we change the wave speed. In fact, in this case, if you increase tension, you will increase wave speed. Okay, so let's check that out. Well, from this up here, if we increase the speed, what's going on the other side? Frequency, wavelength. Right now, we don't actually have a note, so to speak. We don't have a standing wave. We want one, but it's that same 0.8 meters from here to here, and we still want that half wave chunk or quantum. So the wavelength will actually stay the same. What has to happen to frequency? Frequency has to go up in order to maintain this equality. Let's try it here live. Let's turn this up. Boom. There it is. Look at that. Standing wave back at not 16 but 23 hertz. And just in case you're not sure how this connects to an instrument, check this out. Here's our instrument. I'm going to strum this note right here. And then I'm going to change the tension. I'm going to make it more tense. So just like we added weight, I'm going to twist this knob to make it more tense and listen to the note. The note becomes higher. More tension, increases wave speed. Same half wave chunk, standing wave in the string. Boom, frequency has to go up, higher note. How's that for cold? And there is one other adjustment we can make. So I'm actually going to take the tension off, get this thing back to its 50-gram hanger. And of course, 23 hertz is no longer a resonant frequency. Let's get on back down to 16. Okay, looking good. What else can we do to adjust this? Oh, well, the second adjustment is to change the length of the string. So how can we change the length of the string? Well, in our guitar, we have a neck with a fretboard, these little metal raised strips. If you push down, you have then effectively made the string shorter. Well, what difference does that make? So what if we shorten the string? What difference would that make? Well, let's come over here and look at our equation. In this case, the string is under the same tension, so the speed remains the same. If the string gets shorter, that now means that the wave has to fit into a smaller space. So basically, if we look at our standing waves before N, for no motion, it was like this. Now we're going to make the string shorter, N, and now N won't be here anymore, maybe it will be here. And so the string actually gets shorter. What happens to the wavelength? Well, this one, if this were 0.8 meters, now it's 1.6 meter wavelength. In this one, maybe it's shorter, maybe it's only 0.54 meters. Well, a full wave then would be 1.08 meters. So the wavelength gets smaller. Only way to maintain this equality is if the frequency goes up. Let's see if that works. Based on this equation now, Let's see if this actually works. We have a way to pinch our string. Let's put, here, tape this in here. So basically, this is equivalent to pinching the string. We have made the string effectively shorter. Notice 16 hertz is not doing it anymore. Let's try it. Let's go up a little. Oh, bang. There it is. Check it out. 21 hertz. That's pretty cool. We made the string shorter. You required then, the wavelength shrunk, a bigger frequency in order to maintain that speed. Does that actually happen when you play the guitar? Let's see. Here's your guitar. You play that same note. I'm going to strum it down here. Now I'm going to shorten the string by pinching it. You hear that? And as you go, shorter the string, higher the note. Pretty cool. So your instruments really do come down to understanding standing waves and resonance. Check out. So we did our string instrument. Cool. I want to show you this with our pipe instrument. Our pipe instrument also is pretty awesome. Here's our pipe instrument. Now, what I said, geometry. Geometry will tell you what standing waves will fit here. How do we chunk this? So here's how we're going to do it. We're going to need to know how long these pipes are. So here's the pink pipe. There's 30. Sorry, the yellow pipe. There's 30 up to, you got a little parallax going. Looks to me like almost exactly 33 centimeters. And we'll do the pink pipe. Pink pipe, 39 centimeters. You could see it there. Here's 40, just below 40. 39 centimeters. So we know the lengths of these pipes. Now there's something cool about these pipes. Yes, they are instruments, and yes, they actually play pretty well. So we're going to move our generator set up. We're going to make use of this piece of table over here. And here we go. So, we're going to play a note in here, and in fact, we're going to predict the note. Check this out. When you play a pipe instrument, I'll show you something. So, this pipe has got an open end. Here's the other end. Now, how do things fit into that pipe? Let's move our string out of the way. How do waves fit into that pipe? In fact, make this pipe look exceedingly large just so we can easily see this. A pipe like this, when you play, we're going to play this the way you would play a brass instrument. You got to flutter your lips. When you flutter your lips, the air moves a lot. That's flappy air, which means if your mouth goes on this end, mouth, and this is the other open end, the air is going to be fluttery here. Now, what do I mean by fluttery? I mean that if we were to fit a wave in here, you're not going to put a point of no movement here. You want to put that N over here and say, oh, it doesn't work that way here. Because your lips are fluttering, the air here actually flutters. This end actually looks like here, this point, that oscillates between crest, trough, or in the case of sound, compression, rarefaction, compression, rarefaction. So actually the way this works, you're going to fit a chunk in here that starts, that drops down, and you got a fluttery end over here too. The other one is going to be like this. There's actually a point of no movement right here in the middle of the pipe. And over at these two ends, you get points of max movement. Now, I'll tell you what those are later. In fact, I might as well tell you, no movement actually has a real name. N is not for no movement. N actually is for the word node. And at the points where it flutters back and forth, we call those A's for antinodes. So in case you ever see the terminology, going back to this one, we had a no movement node, no movement node. Right here in the middle, we would call this an antinode. The next one was no movement node, node, node. In the middle of them, where you get the max fluttering, antinode, antinode. Okay, anyway, just a little terminology. Here's the cool thing about this. How many waves have we fit in there? Now we're using this for predictability. How many waves have we fit in there? Well, if you want to look at just the solid line, here is, let's say, a crest. It's not really, it'd be like a compression. And here it looks like a trough. We're just modeling it. Crest to trough is only half wave. So this setup is 1/2 wave. Now, if I'm telling you that the yellow pipe is 33 centimeters, what I'm saying is that half wave is going to equal 33 centimeters. And if we want to solve for wavelength, multiply both sides by 2. And so the wavelength here is going to be 0.66 meters, or 66 centimeters. 0.66 meters. Now, what can we do with that? Well, conveniently, in your reference table, you've got the speed of sound. The sound we're making here in this pipe. The speed of sound in your reference table says 331 meters per second. That's actually at STP, which is 0 degrees Celsius. We're at about 20 Celsius. And if you want to convert, so PRT2 says the speed of sound is 331 meters per second. If you want to convert that to your speed of sound roughly at something other than STP, well, you add about 6 meters per second for every 10 degrees Celsius. So if we're about 20 down here, that's 6 times 2 is 12. So this is going to be roughly plus 12. So the speed of sound in this basement is probably about 343 equals some frequency times 0.66 meters. Now, divide both sides. 0.66, 0.66. The frequency of the yellow pipe should play somewhere around 520 hertz. 520 hertz. All right, seems all well and good, but does this actually do anything? Well, let's try it out here. We have a nice little school computer. And here's 520 hertz. Let's play it. Hear it there? Let's stop it. Now, I am going to play Yellow Pipe. Now you'll notice I struggle a little bit until it's almost like you find a rhythm. Once you get that rhythm, it feels right. It flows smoothly. Anybody who plays brass knows what I'm talking about. Ooh. Was that similar? Let's try this. Get this nice and loud here. So we're going to try our 520. You see the, I know it's reversed here on your screen, but try to maybe watch it in the mirror. It's 520. So let's play that while I play this and see. The sound is different. The timbre is different. A number of things are different. But is the note, is the pitch roughly the same? Let's see. Pretty close. That's cool. And so, all right, enough of you. What you'll find is when you have an instrument like a pipe with 2 open ends, or a flute, or a clarinet, or a saxophone, that the chunks that will fit in here are actually also half-wave chunks, except they got that point of no motion in the middle and fluttering max motion on the ends. So they also go in half-wave chunks. Now to play up, on this I can't do it, but if you have an experienced brass player, they can play what's called overtones. They can have the same exact position in the instrument, and they can play a low note or a high note with it. And so what they're doing is actually fitting another wave in. Here's the pink one. The pink one was 39 centimeters. And just to show you, we don't need to do all the math again, you can calculate it. It comes out to roughly 440 hertz. So let's see, maybe it was a fluke with the yellow one. Let's go over to 440. There's always a little error in these, but let's see. Oh, that's a lower note. Let's try it out. Not bad. Not bad at all. And I was not a brass player, I was a saxophone player. I'm used to reed instruments. So, net effect. The goal at the beginning was to convince you that basically objects will only vibrate wildly, loudly, resonate if they are shaken at a certain natural frequency. That natural frequency is determined based on the geometry. Chunks of waves have to fit into the size, the length of that object. And if they do, you found the resonant frequency. This happens everywhere. I talked about it at the last resonance. I'm not going to get into it too much now. That is standing waves. What you saw there, you're creating a wave that looks like it's still. It's not. It looks like it's still. You've created a standing wave. And we'll talk a little bit more about that later. But hopefully you feel convinced that in fact the geometry of the object determines how the chunks of waves fit into it, which thereby determines the note it makes as an instrument or the shakes it has as an object. Earthquake, buildings, roads, bridges, and the rest of that, they all have to consider this now. Road collapses are often because the natural frequency of the ground beneath the road during an earthquake matched the natural frequency of that section of bridge. So all of these things have to come into consideration. The world around you,